So the next thing that we're going to talk about is significant figures, and significant figures or significant digits are kind of integrally linked with how we make measurements and what those measurements actually mean when they're recorded as recorded values. But before we can talk about that, we need to refer to two very specific terms, one being precision and the other being accuracy. And in normal everyday jargon, people use them very interchangeably, but in science, they have very specific meanings. So the precision of a measurement describes the units that you're using to measure something. The smaller the unit that you use to measure with, the more precise the measurement. So for example, you might describe your height as being about 6 feet. Feet are a relatively large unit of measure, so it doesn't tell you very much about, you could be 5'8" and describe yourself as being 6 feet. You could also be 6'4" and describe yourself as being 6 feet. And obviously that's a significant range. If, however, you said you were 74 inches tall, that would be much more precise because you're using a much smaller unit of measure. So precision can alternately be thought of as when you take a collection of data, how close together those collections or measurements are to each other. They may or may not actually be close to the actual number, but when you take a set of data and compare them to each individual other data point, the data points are close together. So let's compare that to accuracy. And like I said, accuracy and precision quite often get used interchangeably, but they mean very different things for us. So accuracy of measurements describes how close a measurement is to the real value. The real value need not be very precise. So the units of the real value might actually be huge. When we look at the size of the Earth, we can look at the size of the Earth in terms of kilograms, even megagrams, and that unit or that precision is really imprecise. But if a measurement that I make of the mass of the Earth or a calculation I make of the mass of the Earth is very close, then that value could be accurate, even though the units are huge. So the accuracy of your answer is how much it differs from the accepted value. So how does this play out in terms of significant figures? Well, let's just jump to one step further, or one intermediate to that, which is looking at actually uncertainty in our measurements. Whenever a measurement is made, there's going to be some uncertainty in the last place of the decimal. And that's because all measurements are not completely free of flaw. Even though you look at a digital display and it says that it's the digital display on the electronic balance says that your beaker is 40.012 grams, that last decimal place is really just an estimate because someone might be leaning on the desk, maybe it wasn't tailored properly, and there are some inherent flaws to the machine itself. Also, as I kind of inferred in the last example, measuring always involves some amount of estimation. And when we look back at our centimeter ruler with the pencil, we said that on the centimeter scale, it wasn't just 9 centimeters. We'd say that it's about 9.5 centimeters. I estimate that last decimal, even though I can't accurately read it on the scale. So the uncertainty, that last decimal place, is only ever an estimate between the graduation marks on the instrument. So how do we record that uncertainty? Well, the uncertainty associated with a measurement can be shown doing one of two things. We can either have an error range, which you may see as a plus or minus value. For example, the mass of a pen is 3.42 grams plus or minus 0.02 grams. The uncertainty is in the 100th decimal place, and the actual mass we know to be somewhere around 3.42. It could be as low as 3.4 grams or as high as 3.44 grams. The other thing we can look at is significant figures, also called sig figs or significant digits. So let's flip back to uncertainty ranges just for a second, because we will see them on occasion. Uncertainty ranges is a range value that can be used to determine where the uncertainty lies in a measurement. That is, what place of the decimal. So when I look at a recording, For example, we've got 3.4256 grams, and maybe that came off of a very, very, very precise electronic balance, but I know the error range to be plus or minus 0.02 grams. That really means that the thousandth or the hundredth position is an estimate, which means that the 3.425 grams, that 2 position is really just an estimate, and everything after it doesn't really mean anything. So that really means that I should be recording that value as 3.42, but we round it off to make 3.43 grams. So, significant figures include, by definition, this is a definition you should know, hint, hint, all the numbers in a measurement that you're sure of, because you know when you're reading a grad cylinder, for example, you get to keep all the digits that you know for sure. And what you may not have done before this year is that you get to keep one uncertain digit, one number that's an estimate. And when we consider what those significant figures are, all the ones that you know for sure are significant, and the one that you estimated also gets to be significant. So here are some rules that you need to know. And I'm going to give you 3 basic different approaches, and you can pick the one that works best for you. So when we look at digits, all numbers from 1 to 9 are always significant. So 1, 2, 5, 7, 9, always significant, which means that all you have to consider is zeros. So in this particular case, we're looking at something called a trapped zero. If I have zeros that are trapped between numbers between 1 and 9, those zeros are also significant. So for example, 501, the 5 is significant because it's a number between 1 and 9. 1 is significant, which means that the 0 trapped between them is also significant. In 3002, the 3 is significant, the 2 is significant, meaning that the zeros trapped between them are significant, so there are 4 sig figs. So, case number 1 of zeros, trapped zeros, those trapped zeros are significant. Now, the second case of zeros are called placeholder zeros. And I always liken this to the case where you have the people at the award shows that get paid to go and sit there, and they're holding a famous person's place. They're not famous or significant themselves, but they're holding the place of someone who is significant, not significant themselves. So looking at 5,200, I know the 5, and I can be fairly confident of the 2, but that 2 might just be an estimate. Remember that I can only keep or consider to be significant one estimated digit, which means that I don't really know the 2 is exactly a 2, so the 0 after it might not be a 0, and the 0 after that certainly might not be a 0 either. So that means the only sig figs that I have in that are the 5 and the 2. The 2 placeholder zeros that are just there to keep the 2 over in the hundreds position is not significant. On the flip side to that, looking at 0.52, I know that the 5 is significant and the 2 is significant, but really, why did I write the zeros on the front? Well, they're just there to make sure I can see where the decimal place is and to keep the 5 over in the correct position. They're not significant or important themselves, they're just there as placeholders. So, to give you a rule, zeros that are placeholder zeros, that's only job is to hold one value in the correct place value, are not significant. Last particular kind of zero that I'm going to talk about is what I call an extra effort zero. So sometimes you make a measurement of 5,000 grams, and it's not just 5,000-ish. You put in a lot of extra effort to make that very, very precisely measured. And so you might end up having some of those zeros needing to be significant. So in order to show that you use extra care in making those measurements, you put in extra effort, zeros or decimals that do not need to be written but are written indicate extra effort and are significant. Over the span of the year, you'll figure out that I'm lazy. If I don't have to write something and I do, there must be an important or significant reason why. So looking at 0.0005, the 5 is significant. What were the zeros in front of it doing? Well, those zeros were only there as placeholders, so 1 sig fig. But 0.0050, I look at this 5 and it is significant, and I look at the 0 after that 5 and I didn't have to write it, but I did, so there must be an important reason why. The 2 zeros before the 5, not significant still. Why? Placeholders. So 5,000, 5000, 5 is significant, but we already know the other zeros are not, placeholders. Looking at the second one, and this is where it's really important that you're really careful with your writing. I look at 5,000 decimal place. Well, 5,000 decimal place, I didn't have to write the decimal place, and it seems like a small piece, but it's important. So the 5 now is significant, and this decimal place makes everything else trapped and significant. So there are 4 sig figs. So here's the second approach that I can give you after you look at all the rules of 0. And here's the way I say it, is that zeros that are only in question if they're leading, i.e. in front, or trailing, meaning that they're behind. And they can be counted as being significant unless, if you take the 0 away, it changes the size of the number. And if you take the 0 away and it changes the size of the number, it means you had to write them and they're not significant. So really, this is just another way of saying that the only number that's not significant is a number that's just a placeholder. Here's approach number 3. And this one doesn't really explain why the sig fig rules are the way that they are, but it gives you a handy way of remembering it. So it's based on geography, and what you need to know is that the Pacific is on this side of North America and the Atlantic Ocean is on the other. So if a decimal point is present starts with P, you start on the Pacific side of the country and you keep going to the right. So you start at your first non-zero number, and any digit till you run out of digits is significant. So for example, if I have 0.059400, you'll notice here a decimal point is present. So I'm going to start at the Pacific side. I'm going to go till I hit the first non-zero number, and every digit after it is significant. 5 sig figs. Looking at the next example, if the decimal point is absent, I start on the Atlantic side, starting on the right, and I'm going to go through the country. Again, you start at your first non-zero number and count all the digits until you run out. So for example, here there's no decimal place. The decimal is absent. So I'm going to start at the Atlantic side, go till I hit the first non-zero number. Now every other digit beyond that is significant, meaning that there's 6 sig figs. You'll understand better why they're important once we go through how sig figs are important in calculations next day in class.